In the first lesson, we saw how to find a power series solution for a second order differential equation. Now we want to take a look at what are ordinary and singular points and how that fits in with our power series solutions. Now, for the purposes of talking about the second order equations, what we're going to do is call the coefficient of the second derivative p, coefficient of the first derivative q, and the coefficient of the function r. And we're saying each of these can be a function of x. So we could have all sorts of things as long as each of these coefficients were a function of x. So we're going to start by simply recognizing that in order for us to even have a second order differential equation, the coefficient of the y double prime should not be a 0. If it is a 0, we refer to the values of x that make that happen as singular points. And likewise, we call all of the other points ordinary points. So really, it's ordinary points that we can come up with a solution for. Singular points, we just have to tread around. We can handle them. We won't be doing that in our elementary differential equations class, but there are ways of dealing with singular points. And likewise, that's all we're saying with this slide. Now in Calculus 2, we talked about finding the interval of convergence for a power series. We're simply going to be using a little different terminology. We'll call this our interval of analyticity. The interval of analyticity, or the interval of convergence, is nothing more than the distance between the point that we're expanding about, our center of our polynomial, and the nearest singular point. Now this is basically saying what we did in the first lesson. We took this second order differential equation, and I showed you in what we called the algebraic method in lesson 1, where we could write the solution to this second order equation as one constant times some function of x plus another constant times some function of x. These are our approximating polynomials, our series solution, if you will. But again, it's two distinct functions with two distinct constants. And this is what we said in the previous slide. The interval of the radius of convergence is at least as great as the distance from the center x0 to the nearest singular point. Now, I'll show you this in the example that we're going to take a look at in a moment. However, for right now, let me remind you that when we graph complex numbers, we use what normally we would call the y-axis as our imaginary axis, and the x-axis as our real part. So if I was graphing, let's say, the complex number 2 plus 3i, the complex number 2 plus 3i would be 2, the real part, and 3, the imaginary part. So this would be the complex number 2 plus 3i. So let me show you how we can use that for finding our interval of analyticity. We want to find the distance from the center, the point we're expanding about, to the singular point. So this is the distance we're looking for if we have imaginary roots. So let's take this example. First off, if we take the coefficient of the second derivative and set it equal to 0 and solve for x, we get these two real values. Now these are singular points. In other words, at x equals 1 and x equals -1, we don't even have a differential equation, so we're not even able to say things about the solutions to the differential equation. However, in this example, we're expanding about x equals 0. So what we've been saying up to now is, if you're expanding about x equals 0, and you've got a singular point at x equals 1, the distance from x equals 0 to x equals 1 is 1 unit. Now the distance from x equals 0 to x equals -1 is likewise 1 unit. Since both of these are the same, that simply means that our interval of convergence can be anywhere between -1 and 1, which would make the radius of convergence a 1. Now in this one, however, the coefficient of the second derivative is 1 plus x squared. Now if we solve the equation 1 plus x squared, we get the two imaginary solutions, x equals I and x equals -I. So if we're expanding about x equals 1, what we need to do is to find the distance. Here is the point we're expanding about. The point x equals I, which is a 0 plus 1i, would be this point. So we need to know this distance. Well, we can find that distance using the Pythagorean theorem. This is a right triangle. This is a 1. This is a 1. So that distance would be the square root of 2. Now likewise, the point -I would be here. We want to know the distance from the center to the point x equals -I. We can use the Pythagorean theorem again, and we still get the square root of 2 as the distance. Now again, those happen to both be the same, not that they would always have to be. But that just tells us that our radius of convergence is the square root of 2, and the interval of convergence would be 1 plus or minus the square root of 2.